大家早上好，非常感谢大家早上抽出来时间参加这个对话科技活动。我们今天请到的是杜克大学的 Chair Professor， 就是首席教授吧，翻译过来，Kishor Trivedi 教授。然后他是 IEEE 的终身会士，就是 Live Fellow， 然后是世界顶级的建模和软件可靠性方面的专家。那么我们把接下来时间就给 Professor Trivedi 吧。大家欢迎。
I'm not used to using the microphone because I have a very loud voice, but I guess I have to use it for the video. Ni hao. I've been told what is good morning, but I forget. So ni hao is easy to remember. And similarly in Japan, Ohio, very easy, right? Anyway, thank you for wanting to listen to me. I hope you don't go to sleep in the meantime. But so my name is Kishor Trivedi, and my laboratory is called Duke High Availability Assurance Laboratory, and I am from Duke University, Department of Electrical and Computer Engineering. Now I'm hoping that this A will become Alibaba. I got the idea this morning that I'm going to propose DAL as an Alibaba laboratory because there is a campus of my university not too far from here in Kunshan. So we could establish a DAL Alibaba laboratory in Duke Kunshan. In any case, brief introduction to the, many of you may not know where is Duke University, so I'm going to give you a little geography lesson. Duke University is in North Carolina. North Carolina is a state in the United States, in the southeastern United States. And there is an area called Research Triangle Park. Since it's a triangle, there are three vertices or cities, Chapel Hill, Durham, and Raleigh. And each of these has a major university. Some of you may know of. Duke is over there in Durham. And the logo of Duke University is that one. And the most important building on campus is the chapel. So if you should come and visit us at Duke, this is the only place to show you. You know, there's nothing much more to show you. There used to be a cigarette factory. It was world headquarters of Liggett Myers. So I would take visitors to cigarette factory. But now that is gone. So the only thing remaining is the chapel. And I already told you my laboratory is called DAL. Remember the pronunciation, DAL, okay? DAL. Can you say it? DAL, okay? And the logo is this one. Now what does this remind you of? Football, no. It's a shield. You know, you use a shield while fighting with the sword, right? Sword in one hand and shield in the other. And there is a reason for using this logo, because in two of the languages that I grew up with, Gujarati and Hindi, the meaning of the word DAL is shield. And it makes sense because if you look at my research, it has been about shielding systems from various bad things happening to the systems, right? So it's very appropriate. Now, of course, there is always some interesting incidents about this. I was giving a talk like this at Tokyo Metropolitan University a few years ago. And in the morning, I had the talk where I told them DAL means shield, right? And the afternoon, we went to an Indian restaurant for lunch. And there we ordered dal, which is bean soup. So this fellow was confused. He said, in the morning, you told me dal means shield, and in the afternoon it becomes bean soup. Well, the difference is this is dal, the other one is dal. Now most people cannot even recognize the difference, but Indian tongue is very flexible. You know, we have many more sounds and many more letters and so on. And the objective of DAL has been not only work with Duke folks, but also collaboration with many different universities and countries, including, of course, Behang, which is where Professor Zhang is from. And since I've been for 43 years at Duke University, living in the Research Triangle, I think of my own work as in the form of a triangle. So I could call this either Dhal triangle or Trivedi triangle, whichever way you want to say. And I think of my laboratory's work as composed of three components: theoretical developments, applications of these theoretical developments, and the tools, software packages that people can use for doing the reliability, availability, security, performance, etc. And so there are some list of things that I think I have contributed to in the theoretical development. And I'm very proud to have worked with many companies to do some very interesting reliability modeling work. And I will be describing these two today in the talk. And I have been also instrumental in developing a large number of software packages that can be used by people for engineering practice, for teaching, and so on. But I also try to put all these things together in the form of books. And there have been blue book, red book, white book, and green book. This is the green book that just came out. So some of the applications that I'm just going to give a list here, out of which two of them will be described in more detail today. I was very happy to have contributed to the analysis of a major subsystem of Boeing 787, and our result was used for certification purposes of that plane. I was also very fortunate to be involved with the analysis of SIP on WebSphere for IBM, and our work was responsible for selling the system to a telco giant within the US. I have also been involved in very heavily since last 15 years or so in a topic called software aging and rejuvenation. And I assume that some of the applications that you are contacted by your customers could well be because the bad behavior of the system could well be because of software aging that is taking place. Group from Behang is very heavily involved in working with us on this. Another very interesting topic is to talk about how to get software fault tolerance done, not like what has been talked about in the books based on design diversity, but what we call environmental diversity. And once again, this is an ongoing research with many universities, including Behang. I have also had some work done on cloud capacity planning with IBM, NEC, and so on. And survivability is another interesting topic that we have dealt with first time with Lucent, then later for virtual private networks, and more recently for smart grid. I have also done work on security modeling and analysis. And most recently, one of my students is working on performance analysis of blockchain for IBM. And there is, of course, standard software reliability modeling and analysis. One student of mine is currently working on healthcare applications for reliability and performance. Actually, that's very interesting. This student, currently, his name is Rafael Fricks, and his father was my PhD student many years ago. So I've been very kind to him to make sure that he graduates. Okay, now I mentioned books, so I can't resist telling you the books update. The very first book I had written was published in 1982, and that is a basic book on teaching probability and stochastic processes to computer engineers, if you will. And it has been quite successful, and it is recently translated into Chinese. And then I wrote a book that is more connected with one of the software package called SHARPE, and it had a red cover. And the third book was much more detailed book on queuing. Notice that in the first book, the queuing is one of the topics, right? So queuing or performance analysis in a much more detailed way is dealt with in this book. And likewise, reliability is one of the topics in the basic book. Now this is much more detailed treatment of reliability and availability with many real life applications in the book. So in fact, today's talk is more or less an overview of the book that I'm going to give you. So far so good. That's a very broad overview of what I have been doing with a lot of people around the world. Now it's clear that most of what we do today somehow depends on computer systems, communication networks, and so on. So we expect them to be highly dependable. So it goes without saying that we want our systems to be reliable and available. So in order to do this, we need methods given a system or system design, methods that will allow us to assess the level of reliability or availability that system has. I have not included performance here, but performance is another component. And the approach is to do this. How do you assess a given system whether it has a level of reliability or availability that you expect it to have? In a broad way, the first method people will think of is actually do measurements on the real system, right? And after the measurements, you need to do statistical analysis to try to determine whether the system has the level of whatever ility you have, performance, reliability, availability, and so on. But quite often, particularly for a very highly reliable system, such as the aircraft, for example, it will take a long time before you can get enough data to be able to have enough measurements to be able to say anything about the reliability of the system. So the alternative to that is a white box, from the black box approach to the white box approach, where we treat the system as composed of many different components or subsystems. And so we are using the internal structure of the system, how it is connected together. And so from the information about the individual components of subsystem, we are trying to put together the behavior of the system as a whole, using a model rather than measurements. So measurements are done at the lower level. And so, of course, you then therefore combine the two. The black box approach is used at the subsystem or component level, where measurements are possible. But white box approach is used at the system level, where measurements are either not possible, very expensive, or whatever. So we combine the two things together. So you can say that the overview of evaluation methods then of system performance, reliability, availability, or whatever can be based on measurements, which can be said that you're doing error or failure data analytics, right? These days everybody wants to say we are doing analytics, right? So, or you can do model based, and when a model is developed, you can solve the model analytically, or you can solve the model by descriptive and simulation, or maybe combining the two. Parts of the model is solved analytically and part by simulation and so on. It's not as well developed, as much utilized as it should be, but simulation is quite heavily used. And analytic models, quite often most people think in terms of closed form answer, but quite often the systems are complex enough that the closed form answer is not possible, but the underlying equations can be solved by a tool. And so that numerical solution via a tool such as SHARPE I mentioned is something that I would like more people to be aware of and use. And unnecessary use of descriptive and simulation can be avoided. So we are going to concentrate on this method, numerical solution via a tool, is what I have been always using most of the time. Occasionally I use simulation, but most of the time numerical solution of the underlying equations of an analytic model using a tool. So if you do that, then analytic models in this context of reliability and availability, and there is similar for performance, that can be divided into 4 types of approaches. One is the simplest one that I will describe first, is non-state space approach. Some people call it combinatorial, and then the state space approach. So first we will explore these two, and we'll find that the difficulties in both of them. So we will then combine them into hierarchical and fixed point iterative methods to solve real problems. All right? And in each of these I will try to illustrate with real system examples. So first, the non-state space type methods in the context of reliability and availability. And so if I look at what people use among non-state space methods, they can be seen as 4 different types of model types or solution types. The simplest one is going to be a reliability block diagram that most people are usually familiar with. And then the more complex one is a fault tree that you may not be familiar with. And even more interesting one is what is called non-series parallel reliability block diagram or reliability graph. In each of these I have real examples. So I don't talk about just theory, but by the way, there is a very interesting quote. In theory and practice are the same, but in practice they are different. Have you heard of that? In theory and practice are the same, but in practice they are different. So I'm going to take first the block diagram. So non-state space methods such as reliability block diagrams, reliability graphs, or fault trees are easy to use. They are very intuitive, and they can be easily solved for system reliability, system availability, system mean time to failure, can be used to find bottlenecks. If your system reliability, availability is not good enough, then what should you concentrate on? These are the bottlenecks, right? Only difficulty is that we're going to assume that everything is independent, right? So assuming that, you can solve very large problems, and relatively good algorithms are known for solving medium-sized systems, if not very large systems. And for each component in the model, you can have a probability of failure, failure rate, non-exponential distribution of time to failure. You can associate repair as well. So all this can be done. So just to show you that these kinds of things have been used, in around 2000, Cisco had asked me to do the analysis of their router 12,000. And at the top level, it was a simple reliability block diagram like this. It had so many subsystems, LC in, LC out, CSC, SFC, whatever they're called, right? So what I'm trying to show you is that block diagrams such as this are and can be used for real life systems. And of course, it turns out that this is only the top level model. Eventually, there will be a bottom. This will be hierarchical, but at the top level, they are, and Juniper, they wanted me to compare Juniper routers availability with the Cisco router availability. And so Juniper router had a very similar structure from the reliability perspective. And then after comparison, I ended up writing a report. They were hoping that their system will show up better in availability than Juniper. It turned out that they were about the same. If I had shown that they were better, my report would be on the main website and so on. But it turned out not so different, and so my report was hidden somewhere. Around the same time, there was a company called Sun Microsystems. Do you remember? Okay. Sun Microsystems asked me to do the availability analysis of their system being designed at that time. And so this is again a top-level reliability block diagram of a Sun Microsystem, a high availability platform. And I always end up doing a paper afterwards. So I made Sun Microsystems write a paper with me, maybe 5-6 years later, based on the work done there. Once again, what I'm trying to show you is the top level. They're all simple reliability block diagrams, like we described. Now, quite often, depending on the industry, we go to another representation called fault tree. How many of you have heard of fault tree? No? Okay. So it turns out that computer and communication industry uses reliability block diagram. But nuclear, aerospace, and safety critical industries tend to use fault-free. It's a sort of a complement. In reliability block diagram, you're looking at conditions under which system is up. In fault-free, you're looking at conditions under which system is down. So pessimist approach rather than optimist approach. And so instead of showing you details of this, let me just show you. This is a GE fault-free example from GE truck. So there are events which are failure events now, subsystem failure events. And the gates are used to combine these failure events, OR gates and AND gates and so on. So the top event is the system failure event. So conditions under which system fails versus conditions under which system is operational in the reliability block diagram. Now, what do you gain by this? Well, first of all, you can have gates which are not gates, exclusive OR gates, etc. You can get a lot more interesting gates. But what is even more interesting is something called repeated event. So this is another fault-free from GE of their ventilation system. But what is to be observed is that there are circles and triangles, right? So this triangle indicates that this is exactly the same event as that. So this is called a repeated event. Repeated event. So you have a lot more power now than a reliability block diagram. And so, but this of course creates difficulty in solving. This is a little more difficult in to solve, because when you come up here, there is there is independence, right? So another fault-free from GE equipment ventilation system, or is it the different one? No, I was just pointing out that fault-free with repeated events, right? Now, even more interesting fault-free is from IBM Blade Center. This is a top-level model of the IBM Blade Center. We will see later that whenever there is red, it means there is a sub-model down below. So this is only a top-level model. So what I have described to you is the use of these non-state space. Now, why do I call them non-state space models? Underlying this, there is a state space. But if there are, how many components here? I think 189 components, right? If you were to do a state space model, each component, suppose, only has 2 states. Then what will be the number of states underlying this? 2 to the power 189. But because I'm not, I have this fault-free model in which I don't have to construct the underlying state space. I can solve it without generating the underlying state space. And that allows me to solve moderate size systems. 500 components I can solve. But if you have to do the state space, it will be 2 to the 500 states at the minimum, right? So the power of these model types is that you are able to solve large systems. Only difficulty is you're assuming independence. Now, these things are incorporated in the tool that I mentioned, SHARPE, which stands for Symbolic Hierarchical Automated Reliability and Performance Evaluator. And it is a formalism that allows you to specify many different model types like I showed you, and install maybe around 1,000 companies and universities. And it is used by people to teach about these things and to do research and in engineering practice. And some of the companies that use these include partial list there. And in fact, Boeing internal tool called IRAP, the core is SHARPE. Core is the SHARPE. So now what I want to tell you is that the next model type, which will come into the Boeing thing, is called reliability graph. So reliability graph is a set of nodes and edges. Edges may represent components that can fail. And we have a source terminal and a target or sink terminal. And we are looking for a path from source to target along which all components are functioning properly. And we are looking for the probability of that. And so this is, and the name for this, the ST connectedness network or network reliability problem. So this is one of the things I had mentioned earlier, namely a non-state space model. And why do I talk about this? Because it was used for Boeing 787. So in avionics, commercial airplanes, whenever a plane is designed, they have to do a reliability analysis of each subsystem, and show this analysis to FAA, Federal Aviation Administration, and there is something similar in China, I believe. Before the plane is certified, right? So the reason I mentioned this is that Boeing had a new subsystem in 787 called current return network. I don't know what it, I'm not an aerospace engineer, but there is a new subsystem that was not there in earlier planes called current return network in 787 Dreamliner. And my students who are at Boeing told me that they could model this as a reliability graph, the source and the target, and a lot of edges in between that can fail. And they called me up and said they're going to use IRAP, which uses SHARPE. I said, makes me very happy. Go ahead and do it. So before we go on, what are the known methods of solution of such problems? One is find all min paths. Okay, what is a min path? So a path is any sequence of edges that gets you from source to target, right? And if there are no repeated edges, that's a min path. So the one method is find all the min paths, and then you're doing a probability of the union of all the min paths. That's your reliability. So find all the min paths followed by a method of computing the union of the min paths. Or there are other methods called BDD, which you may or may not be aware of. It doesn't matter. And yet other methods are based on factoring or conditioning. And the fourth method is Monte Carlo method. So this is the exhaustive list of methods people use. And first two have been implemented in SHARPE. So that's why these students of mine who are at Boeing said they're going to use to solve this problem. I said, it makes me very happy. They tried to use it, but what? It didn't work. Now, I won't tell you a story if I didn't have a solution, right? But it didn't work. So first of all, why did it not work? Well, too many min paths. How many is too many? Can you read this? 4.2 trillion. 4.2 trillion min paths. Nobody can solve this problem, right? But the problem has to be solved. If you want to certify the plane, you need to solve the problem. So they called me up and said, Kishor, we tried to use this, but it doesn't work. Okay, do you have an idea? I said, yeah, there is always an idea. An idea is very simple. And I have a very good student who I can send to you as an intern to Seattle. And we can try and work out. There's no guarantee in all these ideas, right? Research ideas. And the idea is extremely simple. Extremely simple. What is the simple idea? Remember, I'm asking you to compute the probability of a union. Right? Union of all the min paths. Now suppose I take a subset of all the min paths. Then I know that the answer I will get is less than equal to the answer I seek, right? If I have a probability of a 4.2 trillion events union, I'm saying I'm going to take only 29 events from this, let's say. Then the answer I will get will be less than equal to the answer I want, right? Now, in Boolean algebra, if you remember, there is something called a dual. If you have a min path, there is a min cut, right? So if I take, suppose conceptually all the min cuts, and then I take a subset of min cuts, then I will get a bound on the other side. So I will get two bounds, upper bound and lower bound on the reliability. And if these bounds are close enough, I'm done, right? So, of course, now this is easily said than done. So the idea is simply find the upper bound and lower bound, and if they are close enough, I'm done. And my student went there and spent 4 months trying to mechanize this as efficiently as possible, and developed an algorithm for doing this, which the intractable problem was solved in 900 seconds of computer time by this very, very simple idea. All right? So what I'm trying to show you is that many problems in real life, I find, can be solved directly by using the methods that we have, but occasionally a problem comes along that requires development of a new method. And when this was developed, Boeing was so happy that they wanted to patent the algorithm. Now, I never knew that algorithms such as this can be patented, but, but they ended up patenting the algorithm jointly with us, of course. And so we held up the paper until the patent was finished. And so we ended up writing a paper also in European Journal of Operations Research on this topic. But it turns out that much more interesting than solving the problem was another problem. I don't know whether you come across similar things. So when they solved the, finally after the new algorithm was implemented in SHARPE and they took it to FAA said, okay, what tool was used to solve this problem? So they said, we use SHARPE, my tool, right? But then FAA says, SHARPE is a software package, right? Yes. Any software package that is used in the certification process must have used a software engineering standard from Department of Defense called DO 178B. Now, I never heard of DO 178B, and it's 25 different students and postdocs who have worked on SHARPE over these years. Nobody knew what is the software engineering standard DO 178B. So I was struck, what do I do? I have solved the problem, but I haven't solved the problem, right? So I dumped everything about validation of SHARPE that I had in my mind, in papers, thesis. I put it all together, and I told them, this is the validation document of SHARPE. And FAA apparently bought the idea. So otherwise, it's very interesting, very interesting. In any case, Boeing got me to write down for them that I will not give this version of SHARPE with this algorithm to any of their competition, like Airbus or whatever. So to summarize this part of the talk, which are non-state space methods based reliability analysis, what I'm saying is that you can use non-state space methods that provide relatively fast algorithms for system reliability, system availability, system mean time to failure, and to find bottlenecks, assuming that all components behave independently for their failure and repair behavior. And there are a number of algorithms that are already implemented in the tool that you can use. But let me skip that part. But the key difficulty is that in real life systems, there is dependence. There is dependence that failure of one component can affect another component. Repair of one component may require another component to wait, and so on. These kinds of dependencies cannot directly be incorporated in these model types that I described so far. So what do we do next? What do we do next? And the next thing is going to be state space methods. And when we say state space methods, the first thing that comes to mind in this context are something called Markov chains. If you ask my daughters or my wife, what do I work on, they will say Markov chains. Right? That's all they know. So to model various kinds of dependencies, complex interactions between components or within components, Markov chains or more generally state space methods can be used. And I'm going to skip some of these things here. But so we have now advanced analytic solutions from non-state space to state space. And let me show you some examples of state space models. So this is everybody deals with operating system somewhere or the other. Every machine is an operating system, right? So suppose operating system is up and running and it fails. And there might be some delay in detecting the failure. And after failure is detected, what do you normally do? Operating system fails, what do you normally do? Reboot, right? Reboot. So if reboot is successful, then you're back up and running. But it is occasionally reboot is not successful, right? Occasionally, hopefully not so often. And in which case you need to do a patch, right? So now what this contains is delays in various stages of recovery, and it contains probability of unsuccessful action in the recovery, right? So reboot not successful, successful with this probability, not successful with this probability. So delays in various phases of recovery and imperfect actions in various phases of recovery, and two levels of recovery, reboot and patch. Now these kinds of things cannot be represented by fault trees or block diagrams and so on, right? If you look at more details of some of the other, so this is a model that I use for IBM for their application server, WebSphere application server, in which after a failure of the application server, it turns out that there are two different detection mechanisms. One is called workload manager, WLM, another is called node agent. And if the node agent detects, then they will do an automated restart of the app server. And if the automated restart is not successful, they will do a manual restart. If manual restart is not successful, they will reboot the operating system. If that is not successful, they will patch, right? Now, detection by node agent may be successful or may not be successful. Detection by workload manager may be successful, may not be successful. If both of them don't detect, then you have a manual detection. Point I'm trying to make is all this real life behavior of system can be incorporated in a state space model like a Markov chain. Pardon?
The file operation you mentioned is patch. What is patch? I don't know what is patch.
Patch? No, patch is get a new version of the operating system that has fixed this bug.
Okay.
Patch, P-A-T-C-H. Patch or repair, right? Fixing something. Normally you don't fix anything, you just reboot, right?
Okay.
But the point is, you tell me how your system behaves, and I will incorporate that into the model. There is no magic. It's simply, I listen to you, I may ask you questions. Is this what happens? And then I incorporate this. In fact, most of the time, like in this case, when I went into the project, I don't think the people that I was dealing with had any idea of Markov chains or fault trees or anything like that. So I was asking them, okay, app server fails. Is there a detection of this failure? And after one week, my interface will give the question to a lot of people. They'll come back and say yes. And I said, next question, is the detection sometimes fail to detect, right? And then after detection, what happens? Is there a restart? I seed the question. I seed the question. And that's how this diagram was evolved, right? So in this particular case, we have delay and imperfect coverage in each phase of recovery. And these are called escalated levels of recovery. That is simplest recovery first, more complex later, and so on, right? And there are other examples. This is an example from Avaya Bell Labs, in which there was two servers. One was warm and the other was hot. And the server can fail, the software can fail, or hardware can fail, and so on. All kinds of details. Again, talking to the engineers who are familiar with the system and just translating whatever they are saying into a model. So if you look at this, then many people will question if they have heard a little bit or learned a little bit. Like my friend from HKUST, he certainly knows that Lou, right? Lou, yeah. He certainly knows that whenever you use Markov chains, you are making the assumption of exponential distributions, right? Homogeneous continuous time Markov chains, you are assuming that things, time to anything is exponentially distributed, right? So a lot of people question that. Okay, you're using all this, but you're assuming exponential distribution. Well, I say, if you have more information, I can solve the problem. There's no big deal. You can use semi-Markov process, Markov regenerative process, phase type expansion, non-homogeneous Markov chains. So don't despair. If you need to, we can solve the problem. Little more effort. So now, if I try to recollect all the thoughts about the state space models or Markov chains, then I can certainly assure you that all kinds of behavior of fault tolerant systems and all kinds of recovery, repair, all kinds of dependencies can be captured by this approach using Markov chains. And furthermore, although we didn't talk about it here, the performance aspects in which concurrency, contention for resources, etc., can also be captured by such models. And furthermore, you can generalize these models to what are called Markov reward models, which will allow you to take into account degradable levels of performance in different states. And so in some sense, this is a panacea in some sense, right? Everything you want to have. Furthermore, I mentioned to you that the usual assumption of exponential distribution can also be relaxed. So in some sense, everything you want to do can be done by state space models, right? But there must be a catch. What is the catch? The catch is state space, right? The number of states that you need to deal with for any real system would kill you, literally kill you, right? And let me show you how it kills you and what you do about that. So far, so good? But you are welcome to ask me a question anytime and stop me, like you did once at least, right? I'm happy to be stopped and hope to answer your questions. Okay, so key problem with the state space models is that the largeness problem, right? State space explosion of the largeness problem. So I have proposed two different methods of solving or dealing with this largeness problem, one of which I have called largeness tolerance. So suppose that in your model you're going to have million states, let's say. It is not possible for any human being to sit down and draw all these million states and transitions among these states. But it is, suppose I provide you with a higher level formalism that can describe the problem succinctly in a very short one piece of paper or something, and the underlying state space will be generated automatically by the tool. Then you don't have a problem, right? If I can hold million states in memory and solve million state problem, I have no problem, right? So this approach is called largeness avoidance, because large Markov model is not avoided. You're going to generate it, you're going to store it, and you're going to solve with it, right? So what are the different higher level formalisms that enable you to do this? One such is based on stochastic Petri nets. I don't know how many of you have heard, and it's not relevant, but there are formalisms that can describe the problem at a higher level, even a very complex system problem, and the underlying state space may be generated automatically and stored and solved. So let me describe to you the next problem that I dealt with, again from at least not from IBM. And IBM Research Cloud at that time had, so the Research Cloud around 2010 or so, this is what they described the Research Cloud to be, which we capture in availability model and separately in performance model and so on. So this is IBM Research Cloud as they described to me at that time. Okay, it has probably gone beyond that to something else. But the key thing that they told me at that time is that all the physical machines or servers were divided into three pools: hot pool, warm pool, and cold pool. The idea is that power consumption is one of the key cost component for data centers, right, or clouds. So by maintaining some of the machines in a cold status, you are saving power. But of course, but it will take longer to schedule the virtual machines from the cold physical machine. So there's a trade-off between power and performance there. Whereas the machines in the hot pool, the virtual machines are almost ready to go quickly, right? So and similar grouping has been recommended by Intel, I'm told. So I'm only describing the availability model. There is a similar performance model, and then there is an optimization of this also done. But and a lot of other people are following this line of modeling for the cloud. So physical machines may fail and get repaired, and a minimum number of operational hot physical machines is necessary for the system to be called up. And in order to maintain that, sometimes physical machines from the warm or a cold pool may migrate temporarily to the hot pool, and then upon repair they may return to the warm pool or cold pool. So that's the migration makes the migration of the physical machines makes the problem interesting. So we were going to do a Markov chain for this, but if you are interested in thousands of physical machines, the corresponding Markov chain will be quite large, as you can imagine, right? So we decided to describe this model using our version of stochastic P-tree nets, which is called stochastic reward net, and it can be shown within a page, the whole model. And then our tool can automatically convert this into an underlying Markov chain and solve analytically and numerically, as well as the same tool can do discrete event simulation if you like. So, and the description of this model, I'm not going to go through all the details, but it's very, very simple. This is the availability model of a very complex cloud, and the place over there keeps track of how many hot machines currently in the hot pool, number of warm machines in the warm pool, number of cold machines in the, and machines can fail and get repaired and migrate and so on, right? All this is very easily described by a simple graph like this. And at the time I want to run, I will say initial number of hot machines, initial number of warm machines, initial number of cold machines, and the underlying Markov chain will be larger or smaller. I don't care. My description is done, right? Are you with me? And so suppose I were to run this. But before I go on, I want to also mention that there are many other formalisms like this, and some of them based on stochastic process algebras. You can also extend UML and SysML to do these kinds of things and so on, and can generate and store and solve moderate types Markov model, and they can be extended to non-Markovian with non-exponential distributions and so on. So when I try to run this, which I call monolithic model, this is what happens. So when I say 3 here, I mean 3, 3, 3. So 3 hot machines, 3 warm machines, and 3 cold machines. When I say 7, 7, 7, 7, okay? So this is the number of states of the underlying Markov chain, and this is the number of non-zero entries in the matrix of the Markov chain. You see, it seems very nice, but after 7, 7, 7, the number of states is so large that I can't store that in my machine, right? So this is why I call largeness tolerance. So problems with large state space explosion problem that I mentioned to you is somewhat controlled, if you will, or somewhat handled by the methods of largeness tolerance, which simply says I will provide you a higher level formalism from which the underlying model will be generated automatically. But in storing and solving such large models, you have a problem, right? So you need an alternative method, which I call largeness avoidance. So largeness avoidance, basically you're going to solve the problem hierarchically. You're not going to solve the problem brute force in one level. So in our particular case, what we did is the following. So we are now moving into hierarchical composition to avoid largeness. So we will not ever have a single monolithic model. We will have submodels. The submodels will be solved and propagate the answer up the chain until you have the final answer. Now, so I will bring another example from IBM for illustrating this method. IBM has a large presence in Research Triangle Park. That's why I have a lot of stuff from IBM. So let me just present to you that example. So this is the implementation of SIP on IBM WebSphere. What is SIP? Does anybody know what SIP?
That's a protocol.
Session Initiation Protocol, which is used for voice over IP, right? Session Initiation Protocol. So IBM had implemented this on WebSphere, and hardware platform was IBM Blade Center, and software platform was IBM WebSphere. And they wanted to sell this system to a telco giant in US. And telco giant says, we have heard your architecture, it sounds very good, but we need some numbers, we need a model to tell us whether we should buy the system or not, right? So IBM engineers that were involved with this had no idea what that meant in some sense, right? And now IBM is a very large company. I'm only talking about the people that were dealing with this particular project. And somebody told them that there is this fellow Trivedi who can probably help you, right, at Duke. So they came to me, and I helped them solve this problem. And they presented to me this picture. This is the architecture. Solve it, right? Tell us what is the availability, what is the reliability of this system. And there is a lot of story I can tell you on this, but I'm not going to get diverted. But what is main point here is that there are two blade center chassis, and each chassis has 4 blades. And apart from the hardware, the software parts, there's a Linux operating system on each blade, right? And then the application-wise, there's a SIP proxy and app server. AS stands for app server or WebSphere application server, right? And the picture tells you that there are 2 SIP proxies and 12 app servers. Pardon? Pardon?
You mentioned that the body chassis is a cluster, right?
You can say that, yes. It's tightly coupled. It's tightly coupled, yeah. But anyway, so this is the picture they gave me. And then I said, okay, tell me what all things can fail in your system before we proceed, right? So on the left-hand side, I kept track of the physical components failing. On the right-hand side, software components failing. So physical components-wise, each blade center has a power subsystem that can fail. It has a cooling subsystem that can fail. It has blades, 4 blades in our case, right? Each blade has memory subsystem, network interface cards, CPU subsystem, base on which it is mounted, and I/O subsystem. And then mid plane is where all the blades are located, and the network that connects the blades on a chassis. And the software side, there's operating system that can fail. And application-wise, there is a WebSphere application server and a proxy, right? So first, I ask them, okay, tell me what all fails. And then I will ask them, once the failure occurs, what is the detection mechanism, what is the recovery mechanism, and so on, right? Now, so each subsystem was modeled using a Markov chain to capture dependencies within a subsystem. And the overall system was modeled as a fault tree because independence can be nearly assumed across subsystems. And because of this, we were able to solve the problem. So this is an example of a hierarchical composition where a single monolithic model is not constructed, not generated, not solved. Each submodel is built and solved separately, and the results are propagated up the hierarchy. And SHARPE, H for in SHARPE stands for hierarchy. So this kind of hierarchical model construction and solution is facilitated very easily in SHARPE. So this is a high-level fault tree, the top-level fault tree, and it should not be very difficult to understand what is going on here. So remember that from the user perspective, I need at least one proxy to be up for system to be up, right? There are 2 proxies. Similarly, I need out of the 12 application server, if 6 of the application servers are working, I'm fine, right? So let's look at the proxy part. So these AND gates, remember this is a fault tree, right? So if both these are not working, then the answer is 1, and that means proxy subsystem is not working, and that's an OR gate. So if proxy subsystem is not working, system is down, right? So for proxy, each individual proxy to be not working, what does it mean? Either the proxy software part has failed, or the blade on which this proxy is located has failed, or the chassis common part on which this blade is located has failed. So logically doing nothing big there, right? Now, notice that, why did I use a fault tree here? Because chassis common, on the same chassis there are 4 blades located, right? So same chassis common will occur here, 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 right? So it's a repeated event in the fault tree sense. So at the top level it's very easy to describe. Then all I have to do is describe each of these nodes into their own models. So hierarchically, so chassis common, what does chassis common failure mean? That midplane has failed, or the cooling subsystem has failed, or the power subsystem, then the chassis has failed. What does individual blade failing mean? Either the base has failed, or the CPU subsystem has failed, or the memory subsystem, etc., right? And now at the bottom level, I have for each of the subsystem I have a Markov model. So this I developed a mid-plane Markov model. I developed a cooling subsystem Markov model. Again, by talking with the engineers, tell me what happens, right? By seeding the questions and so on, CPU, memory. And you had already seen this one. You had seen the operating system model earlier, remember? You had also seen parts of this model earlier of an app server or a proxy. So all these is put together, and final answer comes out, and the overall model looks like this, right? So if I were to do a single level model for this, I will die. It's not going to be possible. But hierarchically, you can solve the problem, right? And so to summarize this part then, so we developed a very comprehensive availability model in which hardware and software component failures were incorporated, hardware and software failure detection delays were incorporated, software failover delay was incorporated, escalated levels of recovery, which include automated and manual restart, reboot, repair was included. I called it repair here rather than patch. You didn't like patch, right? And imperfect coverage for detection, failover, restart, and reboot was included. And then it turns out that many of the, once you have the model, in order to solve the model, you need parameters, right? What is the mean time to failure of this component? What is the mean time to do the restart? What is, etc., etc. So many of these parameters were collected by experiments conducted in another IBM lab in Annapolis. And furthermore, if the answer is not good enough, you want to tell the designers what should you do. And that is sensitivity analysis or the bottleneck analysis. That was done. But it's also more interesting is that, and I'm not going to show you this, but apart from availability or downtime, they were interested in another measure called defects per million. What is that defects per million in this context? Out of 1 million calls that SIP system is fielding, how many calls will be dropped due to a failure? That was called DPM, defects per million. And the number they wanted is 25 or less, right? Out of 1 million calls. So we developed an entirely new method of doing this computation, which includes interaction between the call flow and the failure recovery behavior. It includes retry of messages and so on. And this then formed the basis of a PhD thesis from HKUST, Subrato Mondal, subsequently. But what was very interesting to me is that because of these two models we developed, they told me very clearly that the telco said we bought the system because of these models. Because they saw the detail with which the system behavior was incorporated in the model. They're not just ordinary models you just put together something with one course in reliability, somebody puts together something. No, this is with a lot of experience, a lot of understanding of the system and the modeling. Okay, so now so we have covered these three, right? Simple non-state space models, state space models, hierarchical. And now sometimes something more is needed, which is next, last part, okay? Any questions so far? Okay, I'm going to get back to that cloud model. Remember the cloud model? IBM Research Cloud Model, which looked like this, based on stochastic P3 nets. And the problem was that I can only solve with 7 physical machines, and people will throw you out. I want my cloud has hundreds and thousands of machines, right? So this is not useful. So what do? Well, this is what we did. We decompose, remember this model, right? We decompose this into 3 submodels. The one for the hot machines, one for the warm machines, and one for the cold machines. But you remember that these 3 interact. They interact because sometimes cold machine will be migrating into the hot machine, warm machine might be migrating into the. So how do I indicate that? Well, I indicate that by adding extra place and transition here, 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 and they will communicate after solving. So solution of this will be providing an input parameter here. Solution of this may be providing input parameter there, and so on. So they will communicate after solving, not at the time of. So this we do. So these are the 3 submodels we develop, and then we draw the communication graph. So hot there, that node is the hot model, hot machine model, warm machine model, cold machine model, and after solving the hot machine model, I will find 2 quantities, one quantity which is expected number of tokens in certain place in that model, which will be the input parameter to the cold machine model and the warm machine model. I will solve the warm machine model to compute something called PW, which I have defined earlier, and that will be needed in the cold machine model, and so on. So after solving one, you supply the answers to the other, and so on, right? So this we call import graph, import graph. The problem is that which one you solve first, right? Because they all depend on each other. So when this happens, what do?
I think we do have a lot of.
Pardon?
I do think we do have a lot of cluster communications.
No. This is not a physical model, right? This is models, and models, after solution of models, you're supplying answer. But what I'm saying is that there is no place to start because everything depends on everybody else. So what you do is you cut the chain somewhere and provide initial values and then keep solving iteratively until everything stabilizes. This is what is called fixed point iteration. So when you do fixed point iteration, there are many mathematical questions. Does the fixed point exist? And is it unique? And how quickly it converges? And what is the accuracy and what is the stability? And there is a lot of PhD thesis work remaining here, right? But in particular case anyway, in solution, this is what happens now. Remember that single level model without decomposition was getting stuck at 777. Whereas I can keep going with the decomposition, no problem. So this is an effective way of solving a complex model, complex system model. And so, in fact, what I want to summarize this is that analytic, well, not this one. So overall, actually, if you, no, this won't work here. I have people in the audience read these charts. It's very interesting, but here it won't work because of that, right? Okay, so what I do when I'm facing the problem, real life problem, let's say Alibaba wants to give me a problem to work on, right, together. So I will sit down with the engineers and I say, let's list all possible components that can fail, hardware and software. And then after failure, what are the detection mechanisms for these failures? And then after the detection, what are the recovery sequence of actions? And which software modules are located on which hardware module? This could be an optimization question later, but in the IBM case, they told me the proxy is sitting here and app servers are sitting there, right? And then after all that, after a lot of discussion, you formulate the model. And then there are different ways of validating the model. And then you need parameters, input parameters to the models, right? This can come from tables or from websites, and sometimes experiments are necessary. And then you solve the model, and I hope that you use SHARPE or SPNP to solve the model, to detect the bottlenecks, to sensitivity analysis, and so on. And basically, most of the time they say, okay, but the answer is 37, let's say DPM. I want 25. How do I do that, right? So what if analysis or bottleneck analysis. So to conclude all this, this is what I believe, state of the art of reliability and availability models. And similar chart can be given for performance. The techniques and software packages are available for the construction and solution of reliability and availability models of real systems. I do believe that these are available. And that this is typically done by decomposition of the system into subsystems, which generally is already available. And then followed by hierarchical model composition is the way to solve the problem. Single monolithic model will never solve your problem. And I have personally used this kind of modelings to compare alternative architectures, as I showed you in Cisco, where I was asked to compare Cisco router with Juniper router. I've done this for finding bottlenecks, like in IBM, answer what if questions, design optimization. At certification time, like in Boeing case, at design verification testing time, like in IBM case, at Digital Equipment Corporation, I don't know, do you remember the company? Do you remember? There used to be a company called Digital Equipment Corporation. It was second largest computer company in the world. It has disappeared. But I was heavily involved in doing availability analysis for Digital Equipment Corporation. So, well, I think that I've said enough. Okay. So this has been talk collected from many different writings. So these are some of the selected references. All right.